very good understanding, at least in one particular context, of what holography is. So the best understood example of holography is called the ADS-CFT correspondence. So what is the ADS-CFT correspondence? It's a duality in the sense that there's two alternative descriptions of the same physical system between, on one side, a theory of quantum gravity with a negative cosmological constant, or in other words, an anti-de Sitter space. Okay, our universe has a positive cosmological constant. That's why it's expanding. Here, it's a different type of universe where there's a negative cosmological constant, which basically means that the universe is a box. Okay, so it's a little bit like this picture here, and I'll draw a different picture in a second that is more realistic for the case of anti-de Sitter space. So it's a duality between a theory of quantum gravity in a space with a negative cosmological constant and an ordinary quantum mechanical system. Okay, it turns out it's a very special type of quantum mechanical system. It's a quantum field theory. In fact, it's even a quantum field theory that is scale invariant, so we call it a conformal field theory, or in other words, a CFT. But again, the details of this are not too important. What's important is that it's a quantum mechanical system where the usual rules of quantum mechanics apply. And so everything that you've learned in your quantum mechanics class applies here. Okay? And so in particular, you can completely understand the quantum gravity theory just by understanding an ordinary quantum mechanics. So it's complicated quantum mechanics, but it's an ordinary quantum. Okay? And let me draw a picture that's more realistic for the case of ADS. So anti-de Sitter space is a box, but instead of being a square box, it's just it's more like a cylinder box. Okay, it's like a can of soup. Okay, and that's what anti-de Sitter space is. And the quantum mechanics, or the conformal field theory, lives on the label of this can of soup. So imagine this can of soup has some label which says, you know, I don't know, best soup in the world or whatever. Okay, and the quantum mechanics lives on this label. Okay, quantum mechanics is where we encode the fact that it's the best soup in the world. Okay, and everything that's inside the can of soup can be reconstructed just from the label. Okay, so this is what the ADS box looks like. Okay, and the quantum mechanics equals the label. And this vertical direction here is time. That's not particularly important. If you've had a class on general relativity, this can of soup is the Penrose diagram for ADS. But this is the idea. Okay. Good. So any questions so far?
Yeah. Okay. So I also have a small question. So what can you reconstruct it from the boundary, like
everything?
The bulb?
Everything you could imagine.
Okay.
So if in the inside of the can of soup you have a galaxy in which there's a planet rotating around a star, and you know you, Kiran, are, I don't know, playing soccer on a field somewhere in Nepal, all of that information, everything is encoded directly on the label. Okay. Of course, for that to work, it means that the quantum mechanics must be a very complicated quantum mechanics, right? For it to have the room to accommodate all that freedom. But yeah, in principle, every single thing you can imagine is encoded here.
Okay. And like, I mean, doesn't it violate this no cloning theorem from quantum mechanics? If you can reconstruct from two places, something like that, same information. Oh
no, not really. The no cloning theorem is something else. Here, here we just mean that the quantum mechanics there's a quantum state, and that quantum state knows about everything.
Okay.
Now, if you're trying to extract information from that quantum state, maybe you'll need to implement some protocols that will be very difficult, and so on and so forth. And there may be some limitations to at which speed you can do it. But the point of holography is that quantum state is all there is to know. You know that quantum state. If eventually you've done enough measurements on the quantum state to know everything there is to know about the quantum state, you know everything.
Okay.
That's the idea. It doesn't mean that it's easy to decode. And in fact, decoding the hologram is very difficult and something that people are working on, but it means that all the information is there.
Okay, so there's also a question from Pramod. Okay.
Sure.
So can you unmute?
My question.
Yes.
Can you hear me?
Yeah.
Can
Hi,
you hear
Pramod.
me?
Yes.
Okay. Hello. So my question is it only the dual representation or dual description in the quantum field theory and in the ADS space, or literally we can create ADS something in ADS from quantum field theory from the from those boundaries of quantum field theory?
So it's a little bit both. It's not really or, it's a little bit both. So, the idea is that you have a quantum system that's very complicated. And that quantum system, if you want, is in some sense creating an ADS universe, in which, you imagine the ADS universe has its own rules, and you can do calculations, compute scattering processes of particles in that ADS universe. And the results that you'll find will be the same as if you had computed them in the quantum system. So that's the sense in which there is a duality. Is that, you could do a computation here, or you can do a computation here, and they'll give you the same answer.
Thank you.
Does that help?
Thank you.
Sorry, I can't hear you.
It did help. Thank you. Thank you for
Yeah.
for answer.
Great. Okay. So this whole idea of holography, which eventually led
There's
to
also other question.
Oh, yeah, another question, please. Yes.
Yogesh, can you unmute?
Hello, can you hear me there?
Yeah, I hear you. I hear you.
Okay, perfect. I want to add a question that Kiran sort of asking there. If that cylinder was something, the relation between ADS, CFT, for example, when we say CFT and quantum mechanics, it lives in the Hilbert space, right? So is it like we are trying to map or something that is inside the cylinder to the boundary of whatever the space is inside the cylinder, thinking that the boundary of that particular space inside the cylinder is a Hilbert space itself, something like that?
Yeah, so very good. So the quantum mechanics has a Hilbert space, as you're used to learning about in quantum mechanics, okay, that we understand fairly well. On this side, there's also a Hilbert space. And the statement is that the two Hilbert spaces are the same. But on the left-hand side here, on the quantum gravity theory here, we have to be careful. Because there's sort of a naive Hilbert space, which is way too big, which has too many degrees of freedom. And there's the true Hilbert space, which has much fewer degrees of freedom. And the idea is that these degrees of freedom of the naive Hilbert space, they're not all independent, really. Secretly, they're overcomplete, if you want. And so the naive bulk Hilbert, so this is a very subtle question, which people are also working on pretty intensely. But if you want, the ADS Hilbert space that I'm going to call naive is not the same as the quantum mechanics Hilbert space. Okay. But there's a ADS true Hilbert space, which comes from taking the naive one and understanding the overcompleteness, which is a difficult question, but something that one can study. This is equal to the quantum mechanics. Okay. And if you want, this one is much greater. The naive one is much greater than the true one. Okay, because it's highly overcomplete. But once you've understood what the true one is, then there's a direct equality between the true Hilbert space and that of the quantum system. Yeah, I hope this helps. Good. Please stop me again if it doesn't. Otherwise, I'll go on. Good. So as I was explaining, from black holes came the Bekenstein-Hawking formula that told us about the holographic nature of quantum gravity. So our best hints about quantum gravity come from black holes, but black holes also give us the biggest puzzles. Okay, and the most famous of these puzzles is the so-called information paradox. And then information paradox is the following, is that a black hole in general relativity is completely fixed by its mass and angular momentum and maybe charge if it's a charged black hole. But it's a very finite and small number of parameters, okay, that completely fixes the black hole. Now, if you imagine that you take a very complicated galaxy with tons of stars and solar systems and people on these solar systems, okay, that are doing stuff, and you all collapse it into a black hole, once the black hole has formed, you lost all the information about these galaxies, right? Because you're only left with the total mass and the angular momentum of the black hole. So you had a lot of information, the black hole forms, and you've lost all the information, okay? And so this is what's called information loss. Okay, and it's inconsistent with the unitarity of quantum mechanics. Because the unitarity of quantum mechanics says that if you have some quantum state and you time evolve it, the new quantum state is the following, is just e to the minus IHT. And whatever information was encoded in the original state is still there in the new state, okay? And you cannot lose information by doing unitary evolution. This is a very fundamental principle of quantum mechanics. Okay, so this is a puzzle. And there's various other forms of the information paradox, some of which we'll discuss a little bit later today. Okay, and what we'd like to discuss today is how can holography or ADS-CFT, how can it help to understand these puzzles? How can holography help these puzzles? And what we'll see is that quantum information and quantum chaos are very useful tools to help us understand what's going on. Okay? Any other questions?
I think there's a question in the chat. Like,
Yes. Hold on. Thanks. This is a great question. So the question is, for those who haven't read it, are the constraints on the boundary different from inside? If yes, then how could we project the information to reconstruct everything inside the boundary? So this is a little bit like the question of the Hilbert space. Fundamentally, the constraints of the boundary must be the same as the constraints of the inside. But the constraints of the boundary, we know what they are. They're well-defined because we're in quantum mechanics. So there's a well-defined list of constraints, for example, unitarity, that we understand. And that gives us a lot of control on the boundary. The problem with the inside, which we call the bulk, is that we're not exactly sure what the rules of the game are inside the bulk. So eventually, if we understood those rules exactly, it would be the same set of constraints because there's an exact duality. But the problem is that we don't understand the rules. So that's why it's very convenient to think about it from the boundary perspective, because the rules are clear. It's ordinary quantum mechanics and there's no wiggle room for anything. We just know what the rules are. So that's one of the reasons why holography is so powerful. Thanks, that was a great question. All the questions have been great so far, so please keep them coming. Hopefully it's useful for everybody else as well. Okay. So today I will, in fact, so when I gave my title, I wasn't exactly sure yet what I was going to talk about precisely. So I left it a bit open to talk about both. I'll say a few brief things about quantum information, and I'll really focus on quantum chaos. Not that it's more important, I think both are extremely interesting, but quantum chaos can be phrased more easily just using quantum mechanics. And so I think it'll make it more accessible, but I'll say a few things about quantum information as well. And in fact, I'm going to start there. So one of the questions that we need to understand in quantum gravity and in holographic duality is how from the quantum mechanical degrees of freedom that live on the boundary do we reconstruct the interior? Oh, hold on, there's a question in the chat. Ah, yes, another great question. The dimensions of the bulk is greater than that of the boundary. So how could the two Hilbert spaces be the same? Well, this is the deep and profound puzzle of holography. Okay, is that the degrees of freedom of the inside, or the bulk, let's call it the bulk, it scales like volume of the bulk, right? Whereas the degrees of freedom of the boundary scales like volume of the boundary, which is equal to area of the bulk, roughly speaking. Okay. So naively, that this looks like this is much greater than this. So how could the two Hilbert spaces be the same? And this is what I was saying before about overcompleteness, is that it's only possible because actually this is very, very, very overcomplete. Okay, the degrees of, when we say the degrees of freedom go like the volume, that's what I called before the naive Hilbert space. And the point is that it's very overcomplete. And the true Hilbert space has much fewer degrees of freedom and actually only an area's worth. I hope this helps.
So is it something like in error correction, like quantum error correction, that you encode in larger Hilbert space, something like that?
Yes, it's a little bit like that. And in fact, error correction plays a very important role in understanding how to go from one to the other. But it's very similar. So the point is that the true Hilbert space is much smaller than what you would have naively thought by counting degrees of freedom in one higher dimensions.
Yeah.
That's the sort of profound thing that's happening here. Very good. So as I was saying, the question is, how do we reconstruct the inside of the can of soup from the label? I told you in principle it's doable, but the question is, how do we do it in practice? And what's the organizational features that you need to understand to be able to do that? And there's a sort of slogan that has come out of holography in the last, I don't know, decade or decade and a half, is that geometry equals entanglement. Okay, and there's many other names that are used. Sometimes ER equals DPR, for those who know what that means, and so on and so forth. Okay, and so the idea is that by understanding the entanglement structure of the quantum mechanics, you can reconstruct the geometry. Does everybody remember what entanglement is in quantum mechanics? If not, I'm happy to give a lightning summary. Let's see, let me just wait 10 seconds and see if somebody wants a refresh on entanglement. If I don't see anything in the chat, I'll assume that, good, you don't know. So I'm happy, okay. So let's consider a two qubit system. Okay, so the first qubit can be up or down, and the second qubit can also be up or down. Okay, entanglement is the fact that there exists states in the Hilbert space that are not of the form psi of the first qubit, tensor product psi of the second qubit. And let me give you an example of such a state. If you do up, up plus down, down, this is called an EPR pair. That's the EPR that I wrote up here. And let's normalize it. Okay, you see that this state cannot be written in the form of psi on the first qubit times psi on the second qubit. It's just not possible. Okay. And the fact that the state cannot be written this way means that it's an entangled state. Okay, and an entangled state means that there's a lot of correlation between the first qubit and the second qubit. For example, if you take this state and you measure the spin of the first qubit and you find up, you know with 100% certainty that the second qubit is also going to be up, right? They're very correlated. Whereas if you had a state that factorizes, the first qubit could be up or down, and the second one is up or down, and they're not related in any way, not correlated. Okay, so entangled systems are very correlated. Okay, so that's what entanglement is. Now, of course, here I just gave you an example with a 2-qubit system. Entanglement structure can be much more sophisticated than just a 2-qubit system, but this is sort of the basic example. Okay, so let's try to understand a little bit better the black hole, the Bekenstein-Hawking formula for black hole entropy from the point of view of entanglement. Okay, so we have some quantum mechanics Hilbert space, okay, with its energy eigenstates, EI. And let's consider a particular state that we call the thermal field double state, which is the following. And I'm going to call the two systems. So let me consider now two systems. Both with the same Hilbert space. And I can write down the following state. How can, sorry, there's a question in the chat. How can particles be entangled? Well, particles can be entangled. Oh, is your question, how do we produce an entangled pair of particles? If that's your question, then there's some measurements that you can make. So, you know, you put particles together, you do some measurements, and then sometimes it happens that the lowest energy one is only for an entangled pair. So then if you do some measurement and keep only the lowest energy ones, you know that you have an entangled pair. So there's ways to produce particles that are entangled, and people have done many experiments. I mean, we even had a Nobel Prize about this recently, right? That's how we entangle particles. And the fact that it's possible is because particles are quantum. That's what makes it possible. Good.
And this, for this ER equals to EPR conjecture, like every time we create entangled particles in the lab, I mean, does it mean that there's OML or? Oh, okay.
Yeah, people create entangled particles in the lab all the time. There's even an industry, you know, people are using entanglement to protect data. You know, so for example, if you want to protect banking data, if you create a bunch of signals through entangled pairs, then you can tell if somebody looked or not, for example. So you know, not only is it possible in the lab, experimentally, but for pure lab purposes, but it's also directly used in like industry and stuff to protect data. So yes, we produce entangled pairs all the time. We've become very good at doing that.
And I mean, how about the ohm hole between them? Like, does it mean
that's much more complicated? That's that we don't. So we can produce entangled particles, but there's no obvious geometry connecting them. Okay, that's a much more subtle thing, and we have no experimental proof of that.
Okay, so that's is it like
way beyond?
Is it only at the Planck scale that you get ohm holes, or okay?
Yes. For two particles that are entangled, it would be at best a Planckian wormhole, which we have no way of observing. That's right.
Yeah. Okay. I see. Cool.
Okay. So good. So I introduced this state that I called the thermal field double state. Why did I do it? Well, you can see that if you now take this state, or rather take the density matrix. So we can take the thermal field double state and take the density matrix. So that's just the ket times the bra. And if we trace over the left Hilbert space, okay, so we trace over En, what we'll produce is the following. We'll produce the following state, sum over En. Okay, and this, if you write it in operator language, is nothing else than e to the minus beta h. In other words, a thermal state. This is called the Gibbs state or thermal state. Okay, and so in this context, the thermal state has an entropy, which is the thermal entropy. But the thermal entropy in this case is equal to what's called the entanglement entropy between left and right. I'm just going to write it schematically. So we started with two systems that I called left and right. We wrote a particular state for them that you can see is entangled. You can see that this state here cannot be written as a direct product of left times a direct product of right. The two systems are entangled. The thermal entropy of the Gibbs state can be understood as the entanglement entropy between the two copies of this thermal field double state. Okay, and here's where we connect to geometry, is that if you look at a two-sided black hole, the geometry looks something like this. There's what's called a wormhole or an Einstein-Rosen bridge, stretching between the left and the right. And there's a place where the wormhole is the smallest here, the neck. And that's the horizon. Okay, so the entanglement entropy of, say, the right region equals the entropy of the black hole, which equals A over 4G Newton. Okay, this gives a different interpretation to how we should think about what the entropy of the black hole is. And it's coming from entanglement between two systems, left and right. And in fact, it's been understood in recent years that this is just a sort of example of a more general formula that tells us that the entanglement entropy of some region is equal to the area of some minimal surface over 4G Newton. And this is called the Ryo-Takenagi formula. Some of you might be studying it in your projects. Okay, and if you think about the thermal field double state, the Bekenstein-Hawking formula is it's an example of the Ryo-Takenagi formula. Okay, and this is about everything that I wanted to say about quantum information for today, because I wanted to focus on quantum chaos. But there's been a whole program in understanding how from the entanglement structure, using things like the Ryo-Takenagi formula, we can completely reconstruct the geometry inside. Okay, and maybe I can just draw pictures that, imagine, so this is like a slice of the can of soup, right? So we had the can of soup. Imagine you slice it at one moment in time. It looks like a disc now. And imagine, I don't know, you have some really cool stuff happening. I don't know, two clouds that are colliding, or there's a bunch of events happening. There's some very rich structure, and we're trying to understand it. How do we reconstruct it from the boundary? And the idea is that we can start probing this rich structure with a bunch of surfaces that probe the geometry, and all of these surfaces are related, to how entanglement behaves in the quantum mechanics system, and that can help us reconstruct the geometry. Okay, so this is really how we get geometry from entanglement. Good. Any questions about this before I move to quantum chaos?
Can I ask a question?
You wouldn't mind if I repeated again the last sentence? Good. So the idea is the following. We have some quantum mechanics system with degrees of freedom, split around this circle here. Okay. And then the idea is that what we're going to do is understand all the entanglement or all the correlation that there is between the different dashes that I put on the system here, understand the entire entanglement structure. And through the Ryo-Takenagi formula, I told you that was given by the area of some minimal surfaces, these red lines that I drew here. And so these red lines probe the geometry and can reconstruct the geometry from the entanglement structure that lives at the boundary. And that's the idea of this whole program that I've worked on a lot, but that I will not discuss too much today.
Okay. Is this for the black hole or for every system?
Every system. There could be a black hole. There could also not be a black hole. You could even test whether or not there's a black hole this way, and so on and so forth. So it's for everything in principle.
Fine, right? From what I heard you, in a boundary, in a black hole, there are two regions of black holes, two areas of black hole. There is an entanglement. So through those entanglement, we are creating the geometry inside the black hole, or?
Well, now you raise a more subtle point that I wasn't really going to discuss, but that I can mention, is that there's limitations to this programs, and there's regions of space-time that you cannot probe through these minimal surfaces. And typically they have to do with the inside of black holes. So there's a question of how do you understand the space-time inside black holes if you cannot probe it from these surfaces, if you cannot probe it from entanglement. And for those of you who have heard these words, the idea of complexity is that complexity is a more refined notion of quantum information, much more subtle and refined, and that maybe using complexity you can probe the regions of space-time that you cannot probe through entanglement. So maybe the original program was called Geometry from Entanglement. We realized that that's not enough because of what you're saying is that there's regions inside black hole that you can't touch. So I think the new version of the program is Geometry from Quantum Information. And that includes other more refined quantities like complexity. And hopefully eventually that'll enable us to understand all regions of space-time. Thanks. That's another good question.
And like we have some projects related with complexity here as well.
Very good. So then, okay, so Lenny Susskind had some papers or talks called "Entanglement is Not Enough," and that was the idea. It's not that entanglement is not useful; it's that just sometimes it's not refined enough to tell you everything you wanted to know. So you need new ideas, and complexity was one such idea. And we don't know if complexity is enough as well. Maybe we'll need to do something even else in other cases, but this is sort of the status.
I think in that paper, like complexity also saturates somewhere, right? I mean.
Yes, eventually, yeah.
But this volume keeps increasing, and
yeah. So there you need to understand, and there's been papers about this, including a collaborator of mine that studied this. How do you understand the saturation from the gravity perspective?
Okay. Like, can you give the reason? Like, what was the reason? Like, why does it saturate from gravity?
It'll be related to things that I say in a little bit. So maybe you can ask me again in 10 minutes. And,
okay, cool. Thank you.
And we'll come back to it. Okay, good. So let me move on to thermalization and quantum chaos. So what I've told you so far is that black holes can be thought of as thermal objects, right? They have a temperature. The thermal field double state that I wrote down describes a two-sided black hole. And so, in fact, this also tells us how to think a little bit about the black hole information paradox or black hole information loss. And that's related to thermalization. Okay, imagine you have some very complicated state in some quantum mechanics that describes, galaxies and planets and so on and so forth. Okay, if you do e to the minus iht, you do time evolution on the state. What happens is everything collapses and you form a black hole. Okay, but if a black hole is a thermal object, then it would suggest that once you form the black hole, you get the thermal density matrix, right? The state has become the thermal density matrix. But this is a big problem because this violates unitarity. Right? Because if you start with a pure state and you go to a mixed state, so if you go from pure to mixed, that's not allowed. Because e to the minus iht, which is the time evolution operator, is unitary, so it cannot send pure states to mixed states. Okay? So the way to think about it is the following, is that it can't be true that a black hole is literally a thermal state. It has to be a pure state. If you started from a pure state, you collapsed into something, you still need to have a pure state. But it might be a pure state that looks like a thermal state to very good accuracy. It can't be exactly thermal, but it might look very close to thermal. Okay, but understanding how that works is the same thing, or is the quantum mechanics version of understanding the black hole information paradox. It looks like you lost information because all you have here is the temperature. That's the only parameter that parameterizes the state. That's one parameter out of a very complicated original state in the Hilbert space. But the point is that that's not exactly true. That's an approximation, and there's corrections to that approximation, and that's where the information is hidden. Okay. So there's a way to phrase the black hole information paradox in this context. So one thing that we'd like to study is the finite temperature 2-point function. So the way to think about this object is, imagine you take a black hole, you perturb it with some operator O at time 0. That'll perturb the black hole, and then you go read off at later time, at the time t, what happened to the perturbation. Okay, so this perturbs the black hole, and this reads off the effect of the perturbation. And if your system thermalizes, what you would expect is that at early time you'll have a big effect, and then eventually everything will rethermalize, bounce off of each other, rethermalize, and equilibrate. Right? And that's what you find. Turns out that you can compute this very efficiently in ADS-CFT, and you see that it decays exponentially with the inverse temperature beta. So the signal looks something like this. It starts off at some value at early time, and then it decays exponentially. Okay? And it continues to decay exponentially forever. And you might think that that's great. That's what you would expect from thermalization, that the perturbation decays. But it turns out that the real situation is more subtle. So let's rewrite this. So O of t, O of 0 at inverse temperature beta is given by the following quantity. So now I'm just rewriting what this thing is. T, O of 0 e to the iht, and then there's an O of 0. And now let me insert a complete set of states here. Let me insert a complete set of states here. Okay, or I should call them M. So this was a sum over n. Now we have a sum over n and m. E to the minus iht when acting here just gives us ent, O of 0. E to the iht acting on em gives us e to the iemt. And then there's the state em. Okay. So we can rewrite this as sum over n m e to the minus beta en plus it em minus em. I've just pulled out the phases now. And then we're left with the square of these things. And let me just call this O n n. This is just the matrix element of the operator, which I can write in the following way. Okay, now I've just written what the definition of this 2-point function is. Okay, I've just introduced a complete set of states and wrote down what the definition is. Okay, but now what you can see is that if you look at the late time value of this correlation function, So let's compute the following thing. Big T goes to infinity, 1 over T, integral from 0 to T, O of T. Okay, so this looks at the late time averaged value of the correlation function. We can compute it. This late time integral is just going to give us a delta function between EM and EN. Okay. So this will just be the following thing. Okay, and this is a positive quantity. Okay, so once again, I'll just repeat. When you do this integral over time and go to very late times, you have a phase that oscillates very rapidly here, and the infinite time integral just gives you a delta function between EM and EN. So it collapses one of the two sums, you're left with a single sum, and this is what you have. So you project to n equals n, so you have a sum over ONN squared, and then this goes along for the right. Okay, and this is positive, and this is positive. So the whole thing is positive. Okay, so that's what this is going to show you that there's a problem. So we had this 2-point function that we computed from the black hole, and it decays to 0 forever. And in particular, there's let's call this thing, I don't know, what do you guys want to call it? Let's call this thing, sorry. This thing, let's call it K, okay? So here's K, which is greater than 0, right? Some value. But we see that the correlation function decays forever to 0. And in particular, at some point, will be smaller than K. Okay, and here's where the problem starts. And everything that happens hereafter is inconsistent, right? And this is a form of information loss. It's inconsistent because we know that the late time average has to be this K, right? But our curve that we're computing from the black hole goes even smaller values and continues decaying forever. Okay, so this is what Maldassina called the form of the information paradox in ADS-CFT. And in fact, even though we can't compute the exact curve, we know what the curve is supposed to look like. So indeed, it does decay for a while. But then eventually, it'll start to have some kind of erratic oscillations. So the curve is going to look something like this. And here's K. And you see that this curve now is compatible with K, right? The late time average value, even if it's still oscillating a lot, the average value is exactly this K. No, K is not related to the minimum energy ground. And so there's a question in the chat: is K related to the minimum energy or ground state energy? No, K is really this quantity here. It's still about high energy states, but it's this thermal. It's this sort of Boltzmann sum weighted by these matrix elements. It's related. It's more related to the 2-point function of the operator, the equal time 2-point function, although it's also not exactly that. Okay, so the question is.
So
yes.
This first plot that you have with the green line, is it from classical black hole or?
No, we don't know how to get this curve from. Well, that's going to be the question. This is what we expect from general grounds in quantum mechanics and quantum chaos.
Okay.
This is what sort of thermalization in quantum chaos tells us the curve should look like. And so that's the point. The point is that, okay, from here on outwards, the black hole answer was giving something else inconsistent. So the question is, how do we get this part of the curve from gravity? Okay, and if we understand the answer to that question, we will have solved this version of the information paradox, right? And we know that the black hole on its own is not enough because the black hole just gives us the curve that decays and decays and decays forever. Very good. And it turns out that this curve, this part of the curve that starts to erratically oscillate, this is related to quantum chaos. So what is quantum chaos? You might ask. Classical chaos, you might have heard of in your classical mechanics class, is the fact that you have systems where if you do a very small change in initial conditions, they propagate to give you very big changes at later times. That's how we define classical chaos. There's a way to think about that quantum mechanically, but the sort of fundamental way that we define quantum chaos is by saying that the Hamiltonian of a quantum mechanical chaotic system is basically a random matrix. Okay? And so any quantum mechanic, seems very powerful and is in fact insanely powerful. It's the biggest form of universality that you ever hear in physics, or at least that we know of until today. Okay, it says that you take any Hamiltonian in quantum mechanics, except if it's very fine-tuned and you're describing a free particle or an integrable system, which there are cases like that that exist, but those are very fine-tuned. If you take a generic Hamiltonian, you could be describing, I don't know, the Hamiltonian of the weather system, or you could look at, strongly coupled electrons propagating, or you could look at, one particle propagating on a very complicated manifold with edges, okay? All of these systems have Hamiltonians that look very different, right? You stare at them, like the Hamiltonian for the clouds looks very different than the Hamiltonian for electrons in graphene or something, right? However, they all have the property that they're chaotic and that their spectrum looks like that of a random matrix. Okay, and this was something that was originally observed by Wigner several decades ago. He was studying the spectrum of nuclei, and he was seeing that, you look at the spectrum of nuclei, it starts looking very much as what people had found from random matrix theory. And he didn't really understand what was going on, but he was discovering really what quantum chaos is. Okay, and in particular, this makes universal predictions. And one of them is level repulsion. So if you have a quantum mechanical system that's not integrable, that's chaotic, and you look at, the density of states at one energy level and the density of states at another energy level, and you coarse grain this over a couple of energy levels, so you average it over a couple of energy levels, there's a universal formula for this, which is the fact that it goes like 1 over E1 minus 2 squared. In other words, eigenvalues of a Hamiltonian don't want to be degenerate. They want to be repelled by a little bit. And this 1 over E1 minus E2 squared is telling you by how much they're repelled by. Okay? And this is what Wigner observed in nuclei back then, is that the energy level is not degenerate and there's some rigidity. Eigenvalues want to repel. Okay, so the spectrum is very complicated, but you cannot have a bunch of eigenvalues that clump up. On the contrary, they want to sort of spread out as much as they can. There's like a force pushing eigenvalues away from each other. And this is very well known in random matrix theory, but it appears to be true in all kinds of quantum mechanical systems. And this is because of quantum chaos and of random matrix universality. Okay? And it turns out that part of this curve, in particular, this rising part here, which people call the ramp, okay, is directly connected to this level repulsion. That's really what's driving the system. So the idea is that, here's our 2-point function. You go to late times. As you can see, there's these phases here, right? So each term in this sum has some complicated phase that when you make t large, that's oscillating very, very fast, right? And so if you go to late times, you start probing the very fine-grained information of the differences of energy eigenstates. And that's what's giving you this crazy erratic behavior. But even if it's erratic, there's a sort of pattern behind it, which is a linear increase. And that's related to the fact that these eigenvalues, even though if you don't know what the exact eigenvalues are, they still want to repel. No matter what they are, they want to repel. Okay, so all the words I've said here, we understand this from quantum mechanics and quantum chaos and thermalization. But the question is, how does gravity know about all of this? Does gravity know about any of this? And how does it know about any of this? Okay. And what's very exciting, and this is now developments over the last 3 or 4 years, is that actually gravity knows something about this. Okay, gravity knows something about quantum chaos. And the new idea, Euclidean wormholes, is that there's other geometries that at late times become just as important as the black hole, even more important than the black hole, and they take over and they drive the physics. Okay, and in particular, they can give us, well, I'll tell you what they can give us. Okay, so I'm going to represent a Euclidean wormhole slightly differently than the other wormhole that I drew for you before. I'm going to represent it vertically. Okay, so this is what we call a Euclidean wormhole. It's different than before, and I should emphasize this difference because here, this direction here, this direction is what's called Euclidean time. If you don't know what Euclidean time is, don't worry too much. It's just that there's a very useful trick that we do when we do thermal physics, is that we take our time direction and we analytically continue to imaginary values. So we take our time parameter and we send it to I times tau Euclidean. We do t goes to I, t Euclidean. And then thermal physics is just encoded in periodicity of this Euclidean time. Okay, so if you take this Euclidean time and you make it a circle, that gives you thermal physics. Okay, some of you might have studied this. If you haven't, it doesn't matter. Take my word for it. So here, these Euclidean wormholes, they're extrapolating between. So we have one boundary at the top and another boundary at the bottom, and the boundary at the top is there for all values of time. We have the entire time circle here. The other picture I drew for you before, which was this one, which was the Einstein-Rosen bridge, is also called a wormhole. So this was the Einstein-Rosen bridge, which is also called a wormhole. But this is a picture that exists at one moment of time. So if you've had a GR class, you've seen Penrose diagrams. So here's a Penrose diagram for the two-sided black hole in AES, or maybe the one that you've seen in your GR class, which is the flat space one. Right? These diagonal lines are the horizons, and the Einstein-Rosen bridge is the geometry that exists at one moment in time. So it's the geometry on this red line here. Okay. One moment in time. So what I want to stress is that this is the picture at one moment in time. The top picture, the vertical one, is a wormhole for all moments of time. And you might not see that that's very important, that the difference is important, but it's very important. It's a completely different kind of wormhole. Okay. So this is very different. In fact, if you try to draw this geometry in Euclidean signature, it just looks like two disconnected disks. Okay, so if you take the previous wormhole that we had and you analytically continue it to Euclidean signature, it looks like disconnected disks, and so it's not connected anymore. Okay. Anyway, you don't need to understand the details, but keep in mind that these two things are different. Okay, and so these Euclidean wormholes are very different geometry. Okay, and the new developments that we've understood is that if you take them into account, you can do better. So what can you do exactly? So remember, we had this curve that decays. And then there was some region where I said there was a problem because it was becoming too small. Okay. Now what we can understand is that if you take into account the wormhole, you can get something that goes like this. Now remember, the true curve was doing something like this. It was erratically oscillating. So we can't get all the erratic oscillations, but we can sort of get the mean of the signal. And in particular, remember there was this constant k that I said that the correlator is not allowed to be smaller than at late time. And in particular, we can make it such that if you take the green and the red lines together, you don't violate this anymore. Okay, so this is better. This is a form of information recovery. It's not everything, because everything would be reproducing the wiggles, but at least the size of the entire signal is big enough. Okay. So this red curve is the wormhole, and this decaying curve was the black hole. And you see that once the black hole becomes too small, it's a better approximation to use a wormhole now. Okay, so we start with a black hole, but then it decays to some value, and then the wormhole takes over. And together, they give you something that's better than just the black hole answer. This is information recovery, or part of the answer, part of the final answer. Okay, there haven't been questions in a while, so let me take a pause and see if there's any questions. Have I lost you completely? Let me just see if there's any questions.
So how is this related with this information loss from page curve type of arguments? Like,
Good. So it's a different. So the page curve is really trying to understand what happens if take some complicated state, collapse into black hole, and let it evaporate. Where did the information go? And the page curve is one way to quantify whether the information came out or not. It's a different form of information paradox than the one that I talked about. Then it's a different problem than this. But the resolution is very similar, is that also in the case of the page curve, what you need to do is take into account wormholes. And it's the wormholes that fix the answer. So the thing that Hawking did when he computed the entropy of the radiation that comes out of the black hole, he just didn't take into account wormholes. And so the puzzle is slightly different, but the outcome, it turns out to be very similar. So I think what this is teaching us is that, gravity looks like it has information loss. But in fact, there's other geometries that have more refined information. And we need to find these geometries and understand what they're trying to tell us. And if we do that, we'll do a way better job at understanding the true physics than if we just kept the black hole. I think that's the sort of message, and it's true both for the page curve and for what I'm saying today.
So, I mean, it's still like this wormholes and black holes, they are taken to be classical objects, or?
Yeah.
I mean, it's the same classical gravity, right? Like,
yeah, it's a solution to Einstein's equation. So it's just a classical, and then, sometimes you can look at small quantum fluctuations on top of the geometry, and that even gives you a better estimate for the results. But yes, it's all sort of semi-classical gravity that knows about all of this.
Okay.
And this is really astonishing, right? Because maybe you can say, okay, gravity is smart, black holes know about thermal physics, the early phase. It's already remarkable that gravity knows about the early phase, but maybe we can say, okay, people have been telling us that gravity is smart for decades now, so that part is okay. But now we're really talking about very microscopic and refined information, right? Energy levels and actual energy levels and their statistics. And even that gravity knows something about. That's really remarkable.
Yeah. So I think there's a question like in chat.
You said Euclidean wormholes and analytic continuation of the. Oh no, no. Sorry, I didn't mean. I hope I didn't say that. So Euclidean wormholes are not the same thing as analytic continuations of the Lorentzian wormholes. If you analytically continue Lorentzian wormholes, you get sort of just disks disconnected. So Euclidean wormholes are really something new. The way I mentioned analytic continuation is first you need to go to Euclidean times. So that requires an analytic continuation in the quantum mechanics, okay? And then you look for solutions in Euclidean time. And that's where you find the wormholes, but they're really new solutions. They're not, so different, let me write it different, and not analytically related. Analytically continued into each other. Okay, not only are they different, but you don't get one by analytically continuing the other. They're just different geometries. Does that help, Sudarshan? Great.
Could you please repeat, how did we get the desired curve from the quantum chaos? I lost you from there. And could you please elaborate how gravity knows about these microscopic stuffs?
Good. Yeah. So the idea is that this curve that we're trying to compute, remember this curve, what was this curve? This curve was the 2-point function at finite temperature. Okay. The idea is that what we expect from quantum chaos and thermalization is that this curve decays for a long time. And then when the signal becomes very small, there's very fine-grained information about the energy levels that enters and starts giving erratic oscillation. Okay. So this curve, this green curve that I drew down here, the green curve, that's what we expect from quantum chaos. It is not what we calculate from the black hole. From the black hole, we calculate this top green curve, which just decays forever. Okay. So the question is, the problem starts here. Here, there's a problem. Okay, because the curve that we get from the black hole is too small. So how do we fix it using gravity? And can gravity fix it or not? And what I'm telling you is that if in gravity you include wormholes, you can fix it because you can get, or at least fix it in part. You can get this red curve that starts increasing again, which eventually will come back to the value of K. Does that help?
Yeah. The answer is black hole. Sorry, wormhole, right?
The wormhole.
It is due to the wormhole.
Yeah, if you add the wormhole contribution, then you're adding this curve, you're adding the green curve plus the red curve. Once you arrive here, the red curve is the dominant thing, so let's just keep the red curve, and then you get this sort of V-shaped thing. You get this plus that. And that's better.
So can you please explain how, from this, how does gravity know about those microscopic stuffs?
It's because I also told you that in quantum chaos, this rising curve here is related to the 1 over E1 minus E2 squared, the level repulsion of energy levels. And so if you take this wormhole answer, so remember again, this is O of t, O of 0, beta. Okay, and you get this linear rising red curve here. If you Fourier transform it to energy space, you will see that it produces this. Okay, so it knows about the fact that energy levels want to repel. Let me just write it. So gravity produces the red curve, and if you just Fourier transform the red curve, you will see this level of repulsion. Okay, and all of this stuff, I should say, was worked out in a very nice paper of Sad, Schenker, and Stanford. Also, Phil Sad had a paper. There's been many other papers.
Is
Okay.
there like some kind of is there some kind of intuitive way to think about this? Like, I mean, how does the wormhole? I mean, they are like connecting interior and exterior of the black holes.
No, I'm not sure there's a very intuitive way to think about this. I think the way to think about it is the following: is that we're doing the gravitational path integral, whatever that means. Okay, we're computing the path integral of quantum gravity. And in the semi-classical limit, we have to sum over all geometries. Okay, and we're very used to the fact that the black hole geometry gives us something useful at early times that we've all accepted. But there's other geometries that may become more relevant at late times. And these wormhole geometries are like that. They're there and they become relevant at late times. And they're encoding different physics. And what they're encoding in this case is level repulsion.
Okay, cool. Thank you.
So if you want here, the black hole is encoding early time thermalization, and the wormhole is encoding late time level repulsion.
And this late times means that the black hole has mostly evaporated already, or?
Oh, sorry. No, I should have said this. This is not the case of an evaporating black hole. Here, we're doing a different setup. We're perturbing the black hole by throwing in, poking the black hole and seeing how it relaxes over time.
I see. Okay.
It's a different setup. Okay. So I'm mostly done because I wanted to. This is the general story, okay? And then the more fine-grained details is complicated if you haven't seen QFTs and CFTs and GR and okay. But I did want to say something a little bit about my own work and what I have done on this topic. So let me just do that, and then we'll finish. Okay. So, of course, in ADS CFT, the quantum mechanics is not just quantum mechanics. It's actually what we call a CFT. So first of all, it's relativistic. It has spatial degrees of freedom, and it's scale invariant. So it's a quantum field theory that's scale invariant. It looks the same at all distances. Okay, it's the kind of system that emerges in phase transitions. Phase transitions are described by critical systems, and relativistic critical systems, that's what CFTs are. Okay. So because of that, all the story that I've told you so far needs to be modified, not profoundly because it's still a quantum mechanical system, but there's much more structure. Okay, so we have to be careful with that structure. So a conformal field theory is described by two things. One is the spectrum of energy levels, which in conformal field theories maps to local operators. So that's, we sort of understand from quantum mechanics, right? It's just the spectrum of the Hamiltonian. But it also has something called OPE coefficients. And these, very roughly speaking, you can think about as the couplings. Okay, so it knows, so a CFT is defined by energy levels and couplings, okay, roughly speaking. And if you know this for every I and K, then you know everything there is to know about the theory. Okay, this specifies everything. All correlation functions, all partition functions, everything can be computed from this. Good. So, very good. So, so the question now is, how do we apply? Oh, and I should say also is that a conformal field theory has a lot of constraints built into it because it's a field theory. And so these things cannot be chosen as you wish. They need to be tuned in order to satisfy the constraints, okay? And there's a whole thing called the conformal bootstrap program, which is trying to understand what are the constraints on these things such that you can have a conformal field theory. And so here we know what to do. So the question is now, how does this whole story of quantum chaos map for CFTs? Is that here we know that the energy levels must be basically like those of a random matrix. But the question is what do we say about these CIJKs, the couplings, the OPE coefficients? What do we say? And the conjecture that I made together with Jan de Boer is that these things are also random. Okay, in what sense are they random? Is that really we should separate the operators into two kinds. If the energy is order 1, then this is just a probe that you can use to perturb the black hole a little bit, like a gravitational wave on top of the black hole. But if EI is much bigger than 1, if you tried to insert this much energy, you would create a black hole. So these are black holes or black hole microstates. These are states that correspond to black holes. Okay, and there's a jargon that we use in conformal field theories is that these are light degrees of freedom and these are heavy degrees of freedom. So now these OPE coefficients have 3 labels, I, J, and K, and I, J, and K can all be light or be light and heavy in various ways. So there's the following possibilities. Okay, and so what we conjectured is the following, is that this is not random. This is about, these things are given by couplings between the probe operators and they can be fixed. Okay, and quantum chaos does not really apply here. These here are actually related to the O and M that I was talking about, these matrix elements of the operators that we saw before. Turns out that they follow something called the eigenstate thermalization hypothesis. These are random. And we also conjectured that without the absence of any structure, that these should be also approximately random. Okay, so in a chaotic conformal field theory, what quantum chaos means is that all these degrees of freedom that are the microscopic description also look like erratic random numbers. Okay, and if you follow that conjecture and you try to compute certain quantities, you can match gravitational geometries, which are Euclidean wormholes. Okay. So the idea is the following: you use the idea of randomness plus various tools that you use in conformal field theories. Okay. And you reproduce gravitational wormholes. In particular, let me just make a drawing. There's a pretty famous wormhole first studied by Maus and Maldacena, which is so this is a double donut. Imagine a double donut with 2 holes. It's called the genus 2 surface. And there's a 3-dimensional wormhole that takes this genus 2 surface and translate it to the bottom. So it's a geometry that looks like this. And we could reproduce this geometry from randomness in conformal field theory. Okay, and we got a nice check. And since there's been more refined checks of this. So it's okay if you didn't understand the details of this, because I'm just saying big words anyway. But the idea is the following, is that the quantum mechanics that arises in holography, the quantum mechanics that arises in holography are very special theories. They're conformal field theories. And we need to understand how to phrase the words of quantum chaos for such theories. But we're getting a good idea of how to do that. And the idea is that there's all this microscopic information that is not exactly random because it's fixed in a given theory, but it's very erratic. There's all these numbers that look like random numbers. Okay. And this pseudo randomness, okay, is related to quantum chaos. And even though gravity cannot extract these individual numbers, right? Gravity could not get the exact eigenvalues of the Hamiltonian, but gravity could get some smooth curves that knows about the statistics of these random numbers, right? So you see, the wormhole, what it gave you, it didn't tell you what E1 is, and it didn't tell you what E2 is. But what it said is that for any E1, the probability of also finding an E2 is 1 over E1 minus E2 squared. Okay, so it didn't tell you what the eigenvalues are, it just told you their statistics. If you have one here, then the probability of having one here is down by 1 over E1 minus E2 squared. Okay, but that's already very refined statistics, and there's higher point functions that you could also calculate, and so on and so forth. And so what semi-classical gravity has access to is the moments of the distribution of all these erratic numbers that are erratic because of quantum chaos. And if you milk that in the right way, you can extract more information, and you can help with information loss because you can produce these curves that start rising again. Okay, and so this is what we've understood over the last 2 or 3 years, but there's still a lot more to do, and so we're excited and that we're going to learn a lot more from this. Okay, I went on for an hour and a half, which is maybe a bit longer than I had planned, so let me stop here and thank you for your attention, and see if there's any other questions.
So thank you, Professor Belin. So if you have questions, then yeah, I think we have a question from Saroj. Yeah, please unmute. Okay. Saroj, like you can ask the question.
Yeah, please just unmute yourself and go ahead and ask.
Exactly. Just unmute.
In the graph, the red line that you draw.
Yeah.
So this does this deviates from the entropy given by Hawking? Or
Yeah, so Hawking didn't really calculate this. Hawking calculated something else, which is related to having an evaporating black hole. So he calculated a different quantity. And what he found is that the entropy of the radiation that evaporates from a black hole continues to grow forever. And what people, so Hawking said, okay, let's have a black hole that evaporates. And let's collect the entropy of everything that comes out of the black hole. And what he found was a curve that goes like this and that continues growing forever. The entropy of the radiation. And you know that that's inconsistent with unitarity because at some point it needs to come down, right? If you started with a pure state, at the end of the day, you collected all the radiation, you have everything, so the entropy must be 0 again. And what we realize now is that this curve that goes down is also due to a wormhole. So slightly different kind of wormhole, but it's also a wormhole. So it's a little bit similar, you know, you have something, so here you had a problem. If you just kept the black hole geometry, you had a problem. And we realized that if you include the wormhole, you do better. Okay, so the wormhole fixes a problem for you. And here it's a different calculation and it's a different problem, but it's also a problem and it's also inconsistent with unitarity, and the wormhole also fixes it. So in that sense, the two things are similar in spirit. But Hawking did not do this particular calculation. This is a version of the information paradox that Maldacena put forward 20 years ago, which is not exactly the same as what Hawking had in mind.
thank you.
I got a question in the chat about the article in Quantum Magazine and the wormhole in the lab. So should I comment on that?
Yeah, sure.
So that's not really a wormhole in the lab, I would say. So what they did is they have there's a system called the SYK model, which is one of the quantum mechanics that appears in ADS-CFT. It's in a particular version of the duality. And the SYK model is sort of a complicated model. And what they did in the lab is, you know, made quantum computers do calculations of the SYK model in the lab. Okay, And the SYK model has a gravitational dual in which wormholes exist, and they found things compatible with that. But that's not really I would not call that a wormhole in the lab, in the sense that the calculations that they made their quantum computer do, we could have also done on our usual computer, and we would have obtained the answer, and then we would have said, oh, that's consistent with a wormhole. So I think the interesting part of what they did is to understand how to make quantum computers be good at calculating those questions, but it's not like they didn't measure a wormhole in the lab, right? They computed a correlation function, which we could have computed in other ways, either analytically or on classical computers, and then the outcome is consistent with a wormhole. But it's not like they didn't take a ruler in the lab and said, oh, amazing, we have a wormhole. That's not what happened. Good. So there's another question in the chat. Holography being the degree of freedom of quantum gravity being outside, yes, and I'm trying to tie what you said about curve predicted by gravity for the statistical nuances of quantum events. And I'm not quite able to. Maybe you could briefly discuss it again. Yeah, so the idea is the following, is that, so we have this green curve, right? And once you reach here, the green curve starts going crazy. Okay. Why does it go crazy? It goes crazy because it's sensitive to the exact eigenvalues. And there's phases, there's very complicated phases that appear that are sensitive to the exact eigenvalues. And because the eigenvalues are erratic, almost random numbers, that's why the signal does this. Okay. So if you want to get the exact green signal that goes crazy, you need to know exactly what those numbers are. However, you can ask a more coarse-grained question, which is, okay, imagine I don't know what the numbers are, but I know what their statistics are. I know what the mean is, I know what the second moment is, the third moment, the fourth moment, the fifth moment, and you keep a finite number of moments. How well do I describe that curve? And you will, the mean of the curve is this red line. You'll also have an idea of its variance, and so if you computed the variance of the red line using gravity, you would have sort of the envelope. And then you would have more refined information. So you would get, you would have a statistical description of the curve here, which is a good approximation to it, but not the exact curve, for which you need to know the exact eigenvalues. Okay, and what gravity can do is figure out these first couple of moments. It doesn't know the exact numbers, but it figures out the first couple of moments. Does this help, Sudarshan? No answer. Oh, yes. Okay, good.
My question is, ADS, CFT, and ER equals to EPR conjecture. They look like kind of a similar thing. In one part, there is gravity, and another part, there is quantum mechanics. So how, if they are similar, in what context they are similar, and in what ways they are not similar to each other? Would you please elaborate this?
Yeah, so ADS-CFT is much more general. ADS-CFT tells you really about a full duality. The quantum system in the boundary equals the quantum gravity system in the bulk. It's a duality about everything. ER equals EPR is more a philosophy about understanding the dictionary between one and the other. So ER equals EPR is to say within ADS-CFT, although you can think that ER equals EPR is more general than just ADS-CFT, it applies to other holographic settings as well. But let's say within ADS-CFT, ER equals EPR tells you that the way you should understand how space-time emerges and how space-time connects various components is because of the entanglement structure. So I would say ER equals EPR is a part of ADS-CFT, but ADS-CFT is much bigger. It's a full duality between everything. There's other questions that we can ask in ADS-CFT that don't have to do with is space-time connected or not through entanglement. What is the value of a scattering process? ER equals EPR doesn't have much to say about that, but ADS-CFT would know. So ADS-CFT is the whole framework, And ER equals EPR is an importance, but it's only a part of that dictionary.
Thank you. It helps. Mm.
Do we have more questions? Yeah, like you also mentioned that you would talk about complexity, like why does it saturate and so on.
Oh yeah, sorry. Yeah, so complexity is a bit similar to this. Complexity, so there's another part of the curve that I didn't talk about here because we understand it much less well, is this part here. This is what's called the plateau. Okay, so the idea is that I talked about the ramp here, which is the rising red curve. But then eventually, you know, the 2-point function should also, its average value should also be flat, right? And understanding how this thing saturates is complicated. And with complexity, it's a little bit similar. Complexity rises for a long time, but eventually should saturate, right? And for gravity in 2 dimensions, just like Satchenker and Stanford sort of understood a little bit of how this works, you know, Iliescu, Mizet, and Sarosi had a paper where they understood how complexity saturates at very late time from a gravity perspective. And it also comes from doing the full path integral and so on and so forth. So, so there's a way to understand the saturation as well. And it's not so different from what happens here. Although I didn't discuss this flat part. Today I was focusing mostly on the red part, the ramp. But of course, there's a lot of interest in understanding the flat part as well. And then if your goal is to understand the flat part, the transition from the ramp to the flat part is not so different than what happens in complexity when it saturates. So there's a very nice parallel. And we understand that parallel for JT gravity in 2 dimensions. We don't understand it generally. It's still an open problem.
Okay, so thank you. So I think like if we don't have more questions, then
I have a final question. It's
Yes.
More of a philosophical question.
Sure.
With all these ideas that we are learning from holography, ADS, CFT, ER equals to APR, so what does it tell about our world, about the nature of reality? What do you think about it?
Good. So there's many different ways to answer this question. A lot of things that were, so you might say, okay, this was all about an ADS. Our universe is not an ADS, so what part of this carries over to flat space, for example, or even to de Sitter space? And this is something that people have studied. And you know, some of the lessons that we learned here are also useful in flat space or even in de Sitter space, which is like an expanding universe. So I think, you know, the particular models and detailed calculations that we did here are not directly relevant, but the lessons that we learned are sort of profound and carry over to many more situations. Okay, so the idea is that there's other solutions of gravity that tell us about refined physics that happens in many cases. Or for the example of the page curve, what we've learned is that, you know, certain regions of space-time can be encoded in other places very far away. And that locality sort of breaks down a little bit. And those lessons, I think, carry over very generally. So I think the idea is that, you know, we study toy models, and ADS-CFT is sort of the ultimate toy models, and not everything is the same, but a lot of the profound notions are the same, or at least are very similar. And so the lessons, those types of lessons, when we learn them, we can apply them in our universe as well. Of course, what would be really nice is to be able to have experimental signals from this. And I don't know if that'll happen in the near future. I like to be optimistic. But of course, it would be very nice to detect some of these things in experiments, although it'll be difficult. But maybe in the context of cosmology, signals of quantum gravity will be there. And then we can see how they relate to some of the lessons that we've learned here.
Thank you so much. Thank you so much.
I hope I answered that question to your satisfaction. Yes, I agree.
So I think like if we don't have more questions, then I think we should thank Professor Belin for this very inspiring talk. And we also have like we also have Professor Nakormi from Kathmandu, like from and Lakshman Dangol. So they are also helping us to run this project. I would also like to thank them for being here. And hopefully, like this talk encourages to do physics in Nepal as well. So
Absolutely.
I think this, yeah.
And
so
it's
this kind of stuff is.
It's
Yeah,
amazing what you guys are doing. Keep it up. I hope you get excited. I hope you're excited about learning more physics. Yeah, keep up the good work. I know it must take some effort to set this up, so I was